Well, good morning, what's left of it. I must admit, I have a sense of following a session of ice and fire, where we first were subjected to ice and then subjected to fire. And as a theoretical physicist, I wonder how in the world can I hold the attention of the audience, especially since you want to get to lunch. So let me try. Do I have I'm sorry, is there here it is, a device I'm looking for. First of all, I want to thank the Society for this invitation. I've actually been a member for a while, but this is the first time that I've actually attended a meeting. So let's get started here. This is the kind of question that people ask when they're children. We heard something about that in the discussion yesterday about how do children actually have ideas? The answer, I think, is yes, because I was 4 years old the first time I told my father I wanted to become a scientist. So I think I'm an example of a child with an idea.
They believed that underneath the whole surface of reality, everything was created by God in a unified way, that if you opened up one little part of it, you could see how everything was connected.
Michael Faraday was someone who, like Einstein, thought in terms of pictures.
Faraday was different from anybody else. He had a flair for understanding his experiments, for understanding what was really going on inside them.
By methodically placing a compass all around an electrified wire, Faraday started to notice a pattern.
What everyone else at the time had been taught was that forces travel in straight lines. Faraday was different. Faraday imagined that invisible lines of force flowed around an electric wire. And then he imagined that a magnet had similar lines emerging from it, and that those lines would get caught up in this flow. It was a bit like a flag in a wind.
But Faraday's great leap of the imagination was to turn this experiment on its head. Instead of an electrified wire moving a compass, he wondered if he could get a static magnet to move a dangling wire.
I've never seen you like this, Faraday. You look like a happy child. I'm shaking, Newman. Underneath, I'm shaking. You see, John? You see? Yes.
This is the experiment of the century. It's the invention of the electric motor. Scale up the magnets and the wires, make them really big. Attach heavy weights to them, and they'll be dragged along. But almost more importantly, he's inventing a new kind of physics here.
That was likely the most important scientific development that occurred in our species' history, because it's the invention of the electric motor, it's the understanding of electricity and magnetism, and it's basically the foundation of all of our high technology to this very day. So if you don't know about Michael Faraday, you might wish to learn something about him. He barely understood mathematics. There's no evidence that he ever advanced to the level of even trigonometry. So to be able to make this earth-shattering, epical discovery in science is a statement about the way the human mind actually works. And because he did not have the mathematical training, he relied on visualization. And that's something all of us do. And that's, again, something that came out of the talk about children, because that, to me, is the secret superpower that our species possesses to create this thing we call science. I, too, think that science is the most valuable thing that our species has created. I define science as the way and the methodology by which we will live more bountiful lives. It's the essential tool to reach that goal, as far as I can tell. But unlike some, I have been worried about science for at least 20 years. I gave a talk in 2005 before the American Association for the Advancement of Science, where I talked about the fact that I feared that faith, based groups would turn science off in the future. It was clear to me that there were trends in this country, even 20 years ago, even going back further than that science is at risk. So I agree with our first speaker that you can lose science, that we can lose science. And the tragedy of that is almost unimaginable. So in the case of Faraday, he actually had a handoff to another scientist named James Clerk Maxwell. And Maxwell built on Faraday's ideas. And one of the things that both Faraday and Maxwell understood is that there are invisible influences around us. We call these things lines of force. Nowadays, we call them radio waves. Because in fact, all of our Wi-Fi is about these invisible waves that exist all around us, and yet we don't actually see them most of the time. There's a time when we do see them. When you snap these lines like a whip, there develops a kink, and if the width of that kink is just right, it will enter your eye, and you'll detect it as light. So the invisible becomes invisible under some circumstances. These are the equations, Maxwell's equations, and I know that a lot of people in the public, probably less of you in this audience, when you see things like this, you want to get your holy water and rosary beads out. But there's no need to fear this the way that lots and lots of people do. If I show you this, very few people have the same reaction. After all, this is something that most of us have access through to the concepts because we can hear. And therefore, there's this level of comfort and familiarity. But if I go back to that previous slide, nervousness emerges once again. So Maxwell and Faraday might be surprised at the image that you see in the middle here. This thing in the middle is an image that came out of two scientists in Birmingham last summer. For the first time, we had the technology as a species to actually see a photon. Now, you'll remember I said when you get a snap, and if the crest distance is just right, you'll see light. But if the crest distance is not just like, you don't see anything. But this technology, based on a quantum material, detected a photon. And this is the image that came out. And so when I saw this image, I was like, gee, well, Maxwell and Faraday would probably be a little bit puzzled, perhaps. And so I started thinking about the first time I met Professor Moniz, who's actually sitting here and was inducted today. He was one of the people on my PhD thesis examination committee in 1977. And what you learn in books is that light looks like this pattern of light and red and purple colors. But I decided, because I speak to the public often, I wanted to give the public a dynamic sense about what a photon would look like. And so I created this movie. It looks like a bunch of wheels and starfish moving along, performing perhaps an elegant or inelegant dance. And the way that this picture should be interpreted is you should think about being out in space and having a friend shine a light beam past you, and you decide to fly through it. When you fly through it, you see that one symbol when it was a perfect circle. And that if the crest-to-crest distance was correct, you would actually detect it as light in your eyes. So let me stop this. That's what that computer animation looks like. That computer animation was invented in 2005. Here's the observation in 225. And so I got it right. Now, what's really interesting about this example of visualization is that those of us who are in the mathematically enabled parts of technical fields, we get this ability to see the universe by using math as our third eye. That's how I beat the experimenters by 20 years to understand what a photon would look like, because I could see it in the mathematics. It took me to think about talking to the public, however, to cast it in that form that agreed with what the scientists found. I want to talk about quantum mechanics a little bit, because you hear the word quantum a lot in society these days. Quantum science, quantum computing, quantum information. What is quantum? So let's talk about that. I recently gave a version of this talk in London, and so I was inspired to think about the bard. And I wanted to use the bard as a sort of a narrative device to try to invite people into understanding how quantum mechanics works. So you all probably remember Macbeth's witches out on the hearth with a cauldron boiling. And so let me use this as a story to explain something about quantum mechanics to you, to try to make it feel more comfortable, more familiar, more something that ordinary people can think about. So imagine that I fill up the cauldron and I don't turn the fire on. I have a little toy boat on the cauldron. I could give it a flick, and I thought the lights were going to come down, but I guess they didn't. But I could give it a flick, and if I don't put fire under the cauldron, the boat simply moves smoothly along the surface in a straight line. And if there were no friction, it would not slow down. But that's Newton's second law. And so there's a situation where you see Newton's second law. Now let me turn the fire on. The cauldron starts to bubble. Again, I put a toy boat on the surface, I give it a flick. Does it move in a straight line anymore? No, because it encounters bubbles boiling up and changing its direction and pushing it back and forth. Those of us like Ernie and I don't see David still here. We study something called relativistic quantum field theory, and in our view of the universe, when we start looking at things, we can imagine, and in fact, our mathematics tells us that particles and antiparticles pop out of the vacuum, just like bubbles on a surface of a boiling fluid. And therefore, the thing that we're thinking about as quantum mechanics can well be, as a device at least, can well be thought about the fact that empty space is filled with these antiparticle-particle pairs, which I'm showing in the middle of this cartoon. Now, a lot of people challenge quantum, well, they used to at least. It turns out the best tested piece of science that we ever had is quantum mechanics. And this number at the bottom here shows that. It's the only piece of science where you can make a mathematical calculation, go to an observation, and they match to more than 1 part in a billion. There's nothing else in science like that. So quantum mechanics, we can incorporate to the 4 forces of nature: gravity, weak, strong, and electromagnetism. At least we can try. But it turns out that the quantum idea doesn't work for gravity. And that's why you may hear from time to time discussions about a quantum theory of gravity. We physicists are looking for that thing. So I'm going to speed up a little bit because I know you're hungry and we've gone a little bit over time, but let me get past. This is my Uncle Albert. He's my hero Maximus in science. So I've tried to model my career to some degree to thinking about how he got science done. And so here are some of his equations, because I just want to run them past you one more time. Think of these as musical scores. And so the question should be, what stories are these scores telling you? Well, they're telling you that we live in a universe that could have started with a Big Bang. That's what you see in this cartoon. You also tells us that gravity is actually the curvature of something we call space-time. And then his equations also tell us that if you look at two things like black holes bumping into each other, they can generate waves of gravity. And in 2014, we measured those things. Now, David's not here, but David Gross and company, oh my God, he is here. David Gross and company back in 1984 invented this piece of mathematics. And I keep telling you, the mathematics is just like scores. So it's like David and his collaborators produced this new score asking questions about gravity. It's in the context of the mathematical string theory, which I'm showing you with pictures. This is not quite the way that David and his collaborators described it. But you know, when you get a piece of music, other composers can give a variation on a theme. So I'm giving you a variation on David's 1984 paper. And what we see is that there are two kinds of waves here. These waves that wind around and the ones that stay still. They're called closed. The first one is called a static mode, and the second one is right mover. We can relate these properties to particles from the mathematics that comes out of this. They look like the kinds of particles we see in the standard model. And so a number of us have been working on these things, and there's a more complicated model that looks like this. This is not quite what David did, but working with a physicist named Warren Siegel in 1988, we did a variation on the theme, and we found out we could put left movers in. So we have standing waves, left movers, right movers. And when you put the left movers in, remarkably enough, these mathematics don't describe theories with 10 dimensions. They describe theories with four. Now, some of you have probably heard that string theory has always got these extra dimensions in it. Well, that's because people don't play around with our variation. If they had, and if they would, they would find that out. Now, this doesn't get us all the way to the end of the story. Let me go back here. This is what the list of standard particles, model particles, look like in nature. Up in the lower left-hand corner, you see what we call matter, the electron, the muon. These are all particles that make up us. Up in the upper right-hand corner are the particles that cause the ones in the lower to stick together so that you get atoms and molecules, chemicals, bonds, and eventually us. But you have to have both of these kinds of things to get to our universe. Here's another picture of a possible universe. And in fact, this possible universe is related to the mathematics that David was using in trying to explain how gravity comes to be consistent with quantum theory. This is called supersymmetry. And this is actually what I do. This is where my core expertise is. As was mentioned in the introduction, I wrote the MIT's first comprehensive book on the mathematics that you're looking at here. So I also did a postdoc at Caltech under the tutelage of this guy. This is Richard Feynman, a very famous physicist. And if someone asks me after the break, I'll tell you some of my own personal Feynman stories. But Feynman pushed us to think about gravity and quantum mechanics, just like Stephen Hawking pushed us. So here's some friends of mine, Chris Hull, who actually co-authored some work with Paul Townsend, who's also a close friend, and this guy here. Maybe some of you have heard of him. Many people feel that he is the greatest physicist of my generation, Edward Witten. Most of the public has never heard of Edward, but Ed is starting to get out a bit now. You can find him on YouTube every now and then, giving a podcast, which is very rare early in his career. But he's absolutely brilliant. And so Ed came up with this thing he called M theory, which was supposed to be the final knitting of the kinds of ideas that David started together with what we need to describe physics, M theory. And one of my other mentors was Abdus Salam, a physicist and also Nobel laureate, Pakistani-born, created a physics center in Italy where I used to spend my summers for 5 consecutive summers. And as a consequence, I had a 300-word Italian vocabulary at one point. And the first book I wrote for the public is named L'arte della fisica. It's only in Italian. But that Italian vocabulary is now mostly gone. However, this guy gave me this set of equations, not just me, but my entire generation. And when we tried to combine this with David's idea, it turns out that the mathematics of this is so complicated, we couldn't even get to the first base. And this problem stymied our field for about 30 years. So that's what the question mark's about, is what's the complete picture here that's consistent with what Feynman wants and Einstein? So at the upper part here, we see these 3 physicists who actually contributed this thing called M theory. We see Feynman saying, well, you folks, that's a nice idea, but you blew it. You haven't gotten the complete picture. Because, see, Feynman gives us a particular way to think about quantum mechanics called the sum over histories. And the upper view is inconsistent with that. So back in 2005, working with a physicist named Michael Fox, I decided to look at these basic equations. These are simple versions. And Michael Fox and I learned how to turn them into pictures. Now, that's actually a very interesting thing because it's visualization. And what we've basically done in my research is to take the kind of equations that started with David and people like that, and we've got visual tools that allow us to understand the structure of the mathematics. And in 2010, the journal Physics World in England was so fascinated by this, they gave us the cover story of their journal. And now I'm going to just show you some pictures of what comes out of this mathematics. They're beautiful. We didn't tell the computer to make beautiful pictures. We just said, take this technique, apply it to the equations that are related to David's work, and see what comes out. Now, the last part of my story is that when you start thinking about equations in terms of pictures, you're doing something that is very interesting because you see, neuropsychologists tell us that the human mind devotes an incredible amount of its energy to the analysis and interpretation of visual data. So if you can take mathematics and turn it into visual data, then you have access to your part of that of your mind to solve the mathematics. And so, in 2020, working with my 2 graduate students at Brown University, we were able for the first time to exploit this ability to turn mathematics into visualization, very primitive visualization, teaching a computer how to visualize. The computers, and I'm going to, like I said, speed up here, give us back a bunch of numbers, but because we know how to take the math and turn it into pictures, we also take these numbers and turn them back into math, and it allowed us, running computer code, to solve a problem that is like the hydrogen atom that has, but in our toy model, it has 4.2 billion electrons, and trying to figure out what they look like. And we use this technique, we solve the problem that Professor Feynman gave us. We're the first people to be able to say the piece of mathematics that looks like it might be the metric consistent with David's and his group's invention of relativistic quantum field theory, including gravity. One of the most mysterious things about our work, however, is that we also discovered something else. Namely, in order to make these kinds of mathematical equations work, error correction enters them. I don't know how many people here are familiar with error correction. I know at least one person yesterday is very familiar with error correction. It turns out error correction is actually part of this picture making. And that means that we, for the first time, have discovered the possibility that there's a law of physics, not in computer science, not in something that we humans do, and maybe with only the other example being genetics, which we actually heard something about yesterday, but error correction may well be part of the laws of physics. And that's what happens when you let people from different demographics enter your realm of doing physics. Thank you.
Pictures, yes. Thank you, and marvelous science. Insofar as I can follow it, I'm impressed, and I'm sure that there are people here who can ask better questions than I can. So please raise your hand. The microphone will come and say who you are and where you come from. Yes, here. There's a question right here. Thank you.
Betty Ruth Walter, Philadelphia, and I'm wanting to know if you have consulted with Sheldon Cooper on the development of these pictures.
So I've never actually seen The Big Bang Theory. Part of the reason is because, well, my wife is a physician, so she has some opinions about the COVID experience we all went through that I think are at variance of things we've heard earlier today. But she tells people that her husband makes things up for a living, but because it's mathematics, no one can tell him it's wrong. So how do I feel about Sheldon Cooper? I've never actually seen the character, and we in my family don't watch the show. We've never watched the show because my wife claims, and she's been asked this question many friends, she claims that the show makes fun of our family. And David knows my wife, by the way.
Alan Spradling, Baltimore. Well, when Einstein, did general relativity, there was this famous experiment where they measured the bending at the next eclipse, whatever. And the big criticism of some of the physics that you've been telling us is just it doesn't have an experiment that could just show that all your beautiful stuff is right. And because you seem to be getting closer to such a day, do you see that that is going to be possible? That could turn everyone onto your side of understanding that this is the right direction for physics to be going?
Well, I'm not so arrogant to be able to say that's actually something that's I'm wedded to. I can tell you the following. Well, first of all, on the first part of your question, I actually wrote a book 2 years ago, no, now 4 years ago, called Proving Einstein Right. And it's actually, it's not about Einstein, it's about the astronomers that you're talking about. We followed them over the course of a decade. My co-author is a novelist, because I always wanted to write a book like David Sobel's Longitude, and I knew I couldn't do that alone. And so I have this book out there that anyone can go read. So I know this history that you're talking very well. What I can tell you is that I am, I guess you would call me a concrete physicist, in the sense that I understand that where I do my work is not necessarily in reality. In fact, I call it mathicality, because it exists between mathematics and reality. And it only becomes reality when the high bar of science is passed. And that high bar is very simple. Can you measure? Can you observe the implications of it? And so until that happens, this will be beautiful mathematics. It will probably give us some hints of new technology, because I showed you the beginning about Maxwell's equations, and the reason for that is that when Faraday completed his visualization of how light works, there was 15 years before he could convince the rest of the scientific community that he's right. And so I have been of the opinion that if string theory, because that's really what I've been talking about here, is what's called string theory, that if string theory is ever accepted as a piece of reality, as a piece of real physics, it will only come about from a confluence of many different sorts of observations. I don't think we're ever actually going to see the strings themselves, because the minuscule nature is so extreme, but we can see the implications of that and possibly find some predictions. I can give you one prediction, by the way. It turns out that the kind of string that, the variation that I did on David's work, that particular set of mathematics demands dark matter. It is mathematically inconsistent with those equations unless dark matter exists. Well, we got a lot of experimental evidence that dark matter exists.
One quick question in the balcony.
Thank you very much. Semir Zeki, University College London. I'm sorry, I'm mathematically illiterate, but I got the impression that you're implying that there is a connection between gravitational laws and quantum mechanics. This is an article of faith. But since this has been pursued for so many years and nothing has been found, I wonder whether you would consider the possibility that there isn't a good relationship between the two. Whether we are asking the wrong question, not we, but I mean the physicists.
Well, I agree that other people are free to ask different questions. It would never forbid people from doing so, but since I have a limited time here on this planet, I believe that time to be very valuable, and therefore I don't try to spend it in ways I think will be unproductive.